Welcome to this lecture 20, which is on insulators for overhead lines. Now, all of you must have seen, in fact, while traveling in a train or while going to any countryside, the transmission lines and these various blackish looking objects which are insulators. In fact, why do we need insulators? Because lines are live, so they should not come in contact with the poles, with the towers, with the cross arms. So, what we do? We suspend lines from insulators. Now, insulators are required for overhead lines, and all those conductor is suspended from insulator, and it is supported by towers or poles depending on the voltage. If it is a very high voltage, extra high voltage, then there are towers. You must have seen towers in open space while traveling, etc. Poles you can see even inside the city, even inside the campus. Now, span between two towers is a very critical factor. There is the economics involved in it. You can't have a tower after every 4 feet, but you can't have a tower after every 4 kilometers also. So, what is that ideal span which you should have between two poles, between two towers? It is a very important topic in design of transmission lines, and you are requested to read T&D handbook, transmission and distribution handbook by Westinghouse. If you need to go into details of tower design, this topic is covered there. However, I can tell you the mool mantra which guides this is the span between the two towers is dependent on allowable sag in the line. I hope you understand the sag. This wire is cannot remain tight all the time. It will slowly get loosened and a sag will form. I will show you the figure here. Like this it will be. This is ground, this is pole, and this is conductor, and it will be like this, and this is the called sag. Now, this sag should not be so much that the wire touches the ground. It will be highly undesirable, unsafe, and it can cause accidents. So, the span roughly comes about 370 to 460 meters, less than half kilometer. Insulators are made of glazed porcelain or toughened glass. These are the two main materials which are used to make insulators, because they have an ideal properties of an insulator. Now, insulators are designed for a given range of voltages. Voltage varies from 220 volts domestic to 765 kV or 800 kV in India. Outside it is 1300 kV. We have not gone beyond, because there is no necessity. If at all Western world wants to reduce the use of energy and not increase, because they have already reached the limit beyond which they just can't go, because they are doing everything by using electric energy. Nothing is left where electric energy is not used. So, and their population is almost constant or decreasing. So, their demand is not likely to go up at all. Now, maximum voltage per insulator is 33 kV. The insulator is designed for 33 kV. You may ask me questions, what happens if the voltage is more than 33 kV? Well, we repeat that and we have several insulators rather than having one. It is a modular, like photovoltaic. If you need more, then we go for more 1 megawatt or 1 watt or 10 watts or 100 watts, depending on what is the cell size in photovoltaics. Even in power plants, big power plants, you do not have one unit of total capacity. You may have 5 units of 100 megawatt each. You may have 5 units of 200 megawatt each. Even Bhakra has 12 units, 6 on east bank and 6 on west bank. Types of insulators. There are only 3 types so far: pin type, suspension type and strain type. Now, pin type, one piece is up to 25 kV. If it is more, you have more pieces, but it goes only up to 50 kV. Why? Why not more? It becomes uneconomical for higher voltages. Pin type. Now, these are the 2 diagrams. The left hand side is pin type and right hand side is suspension type. Well, there are repetitions of these units if required. I have shown just one unit for space constraint, otherwise the whole slide will be full of this. And this is a metal link, this is a disc, and here is the conductor. Since conductor is suspended, this insulator is called suspension insulator. Suppose you have a 400 kV transmission line, which you have in our country. Then we can have 19 discs of length 3.84 meter each. So, it is a gigantic structure. You may not see it because it is in jungle, 400 kV line will not pass through Chandni Chowk or New Delhi, that will pass in somewhere in the isolated areas. Distribution of voltage along the insulator string unfortunately is not uniform. This is the main problem. Which unit is most strained or stressed? Closest to the conductor, and that unit is called line unit. Since in this figure there is only one, so this is called line unit. And this is most stressed. Suppose there are 4 units, this is the least stressed, this is more than that, most. This is a line unit. This is a 4 string in suspension type insulator. Well, you can have a simple mathematics and show that indeed it is the line unit which is the most stressed. You can see any book. When suspension type insulators are kept in a horizontal position rather than a vertical position, that is called strain insulators. This is a special variety like your slack bus. they take tension off the conductors, and they are used, since they are special conductors, I mean insulators, they are used in special situations. What are those special situations? Dead ended lines, roads, river crossings, bridges, and so on. Wherever you feel that this is the end, you cannot take the line further. Up to 11 kV shackle insulators are used for this purpose. Now, voltage does not divide equally across various units of string of insulators as the capacitance changes from each unit to each unit, and that is why voltage does not get, suppose the total overall voltage is V 400 kV. Now, these 4 units will not have 100 kV each across it. It will be 70, 90, 180 and then 220, something like that. So, the lowest unit being the most stressed, that is the meaning. The V1, V2, V3, V4 is not equal. V1 is less than V2, is less than V3, is less than V4. V4 is across the line unit. Capacitance between the metal parts of the insulators and the tower structure is the main reason. Okay. Same thing I told you, V1 is less than V2, is less than V3, less than V4. How non-uniform is the distribution is given by an index. What is that index? That is called string efficiency. There have been, you must have solved many problems in your undergraduate where they ask you to calculate string efficiency. A string efficiency is defined as voltage across string divided by n times V line unit. N is the total number of insulators. Conductor is always 1 into V across line unit, which is maximum, and that is why the efficiency will be less than 100. Sorry, less than 100. Higher the efficiency, better it is. How can you mechanically achieve this higher string efficiency? By having a larger, longer cross arm. However, every good thing in life is at a price. The price you have to pay is more cost, inconvenience to the public, and there is no space, just there is no space. There may be certain houses nearby, or train may be going nearby, or telephone lines are going, interaction, radio interference and so on. But definitely if you can achieve that, you will have a voltage distribution more uniform. What is grading of units? The process by which you can achieve this equalization is called grading of units. If you do that, what happens? If C1 is 5 times capacitance, C2 becomes 6, C3 becomes 8 and C4 becomes 11 and so on. Remember, we have talked about 19 piece suspension insulator. By the time you reach C19, it may be some 120 C. So, it looks so ugly. Each unit is so different than other. And it is not a question of looking ugly. What about the inventory? What about the the replacement, the standby unit? You have to have for each unit one standby, which is very bad. Who will spend so much money? Where is the space to store all these units just because you want to equalize the voltage. But if you do this, this method of grading is called capacitance grading. If you at all do this, if you are adamant, you said no problem, I have a lot of money, I have a lot of space, I will store them, money is no problem, then such a method is called capacitance grading. This is what I have written here, and you will have a perfect voltage distribution, equal distribution. Otherwise, there is a second method, because this first method is uneconomical, impractical. You can't have a 19 different sizes of units, it looks so odd. Suppose you have to have 3 doors in front of your house, if all 3 are of different sizes, different shapes, different look, you will feel something wrong with this man. You can't do that. So, with another method called static shielding, guard ring. This is a guard ring, and you have a connections here, and you whatever values of this x, y, z you can compute, and that will see to it that the voltages are equal, exactly equal. This is much more practical than the earlier method, and this was being used in practice. I think with this we finish this topic of insulators. Sky is the limit, you can go on reading about it. My aim here is only to briefly introduce the topic, brush up your knowledge, so that if anybody asks you questions about insulators, you should be fresh and you should be able to answer. Now, next we go for mechanical design of transmission lines. A mechanical design means what is not electrical. Electrical design is separate, where you have decided the number of conductors, bundles, the currents, the pi model, T model, regulation, R factor, losses, power carrying capability, etc. That is your electrical design. What is mechanical design? Mechanical design means for high voltage you have to design towers, for low voltage you have to design poles, and these structures support the conductors. Now, why there is a sag in conductor? It has weight, it is not weightless, you are not in space, you are still surrounded by atmosphere, and so there is a gravity, and gravity pulls everyone below. So, these conductors are no exception, and they will sag or dip under its own weight. Here is that figure which I had drawn earlier also, called span. Now, wind also plays a part here. The wind load acts horizontally, and its own load acts vertically. Now, in winters in certain countries, ice is also formed. Maybe in India we do not have that problem, barring Badrinath, Kedarnath, Kashmir, Leh, those hilly areas. I do not think there is an snow that does not fall in most part of the India. There is no snowfall in Delhi. Nobody has said that today there was a snowfall in Delhi. When snow falls, it gets deposited on conductors, and that increases the weight of the conductor, and that is why it is written here ice load. This is why I have written here varying weather conditions, varying air temperature. So, conductor tension will also vary. If it is too windy, then there is a problem, sag will vary. Why do you need knowledge of sag, maximum sag? We need to have minimum ground clearance, otherwise it will cause accidents. That library has a copy. The span is 300 meters. This is a span. Now, you can write these equations as we might have done earlier. T is a tension, H is a horizontal tension, 1 plus omega square L square upon 2H square. Y is equal to omega x square 2H, and sag is given by omega L square 2T. T is roughly equal to H. So, this quantity is very small. So, the sag is, it is not sag, span. Span is x plus omega square x cube by 6t square. In fact, this is half the span, if you remember what you did in your undergraduate. This is half span. Half span conductor length is 1 plus omega square L cube 6t square. Sag should be less than 10% of the span. Span is 300 meters, sag should not be more than 30 meters, otherwise there is something wrong. How much ice can be there? 0.5 centimeter thickness or more. Then we say there is ice, and you should consider that ice. What will happen because of ice forms around conductor? The weight will go up. Weight will go up, sag will go up, because sag is precisely because of weight. If the conductors would have been weightless, there won't have been any sag. If you add wind pressure to the weight which acts horizontally, the equivalent weight of the conductor is given by WC plus WI whole square. What is WC? Conductor weight. What is WI? Ice weight square plus WW is wind. Now, there are places in India where there is no wind, almost stand still. On some summer days, if you get up early in the morning, nothing, not even the trees moving at all. So, that is a condition where wind is not there. In fact, the whole country is divided into 15 agroclimatic zones. If you have been a student of atmospheric sciences in this institute, you would have learned more about this. Storms, oceanography, sea storms, earthquakes. This very earthquake engineering is a separate branch. It's a very important branch. So is atmospheric sciences. So, here also atmospheric science plays a great role, and the whole country is divided into 15 agroclimatic zones, and we are in semi-arid zone. Tomorrow somebody may ask you, Delhi is under which zone? Delhi is under semi-arid. It is not arid. Arid is Rajasthan, that is the desert. What is stringing chart? Does anybody remember? If you are asked a stringing chart in an interview, that is given. Prior to that, were you knowing this? You are knowing? Good. So, at least one gentleman was knowing it. If you plot tension and sag on two vertical axes or y axis versus temperature in degree centigrade, always mention units. Temperature can be Fahrenheit, temperature can be Kelvin, temperature can be degree centigrade or degree Fahrenheit. So, temperature in degree centigrade 0 to 60, because beyond 60 it is highly unlikely the temperature will be on the earth where we live. In fact, in Iraq, when temperature crosses 50 degrees centigrade, they declare it to be holiday. This is a standard rule in Middle East. The moment temperature crosses 50 degrees, even here the schools are closed before time if the summer is severe. Instead of 15th May, they close it from 1st May. Many times government has done, and the reverse happens in winter. If the winter is too severe, they may delay the opening of schools after Christmas, because they don't want young children to be exposed to this the vagaries of the weather. I don't know whether you know, in our days in village, when we wanted chutti, we used to put water on the bench when rainy season. Sir, it's all wet. Where do we sit? Okay, chutti. So, this tension in kilogram and sag in meters are plotted like this. With temperature, tension drops, but sag increases, which is quite understandable. There is an expansion in the conductor. Expansion means more sag. But luckily, the difference is not much, though I have not scaled it the way it is scaled x axis, y axis are not scaled. But you can see this stringing chart in Westinghouse book or any design book on power system. There is one very good book on power system design by Begum Mudre. So, that is a person who passed his lifetime in Canada, then he went to IIT Kanpur, and now I don't know where he is, he must be above 70. So, that book gives you a very good account of power system design. People may not like such courses, but they are the courses which are more practical, because this is what you have to do if you join State Electricity Board, BHEL, NTPC, Power Grid. You have to all the time think of designing new system or improving the existing system. With this, ladies and gentlemen, we also finish our sag and tension part of this lecture. The third capsule in this is on grounding, neutral grounding. Especially we are more interested in. Now, grounding is a very important topic is in electrical engineering. In any circuit, you have to first see where is the ground, what are grounded. Even while doing practical, you see what is ground. This is very important from safety point of view. You see, that is why we have a 3-way plug, pin and all those things, live, neutral and ground. Especially when you have done fault analysis in your undergraduate, you must have heard 3 chapters, one on symmetrical components, one on balanced fault and another on unbalanced fault or unsymmetrical faults. What is wrong in unbalanced operation? That is more practical. See, we often say in practice, he is not showing a balanced behavior. There must be some perturbation. He must have got a letter from home or something, some news which is not good. So, he or she gets perturbed, or someone must have banged him, or he must have had a quarrel with somebody, That is why you show a different behavior on that day. So, it is unbalanced operation. So, why power systems show unbalanced operation? Because faults take place. Otherwise, why should it show unbalanced operation? if you see in your houses, the supply is given in such a way that there is a balanced. One phase here, one phase here, one phase here, and ultimately it's overall balanced. Even you try to distribute work in a balanced way, if you are head of the department, you don't just load one particular technician or one particular teacher, hey, you teach all the courses, others enjoy. No, he tries to balance. Everybody gets 6 hours per week or 3 hours per week in a center, in department 6 hours per week. So what you are doing? You are trying to achieve a balance. We say in practice it's a very balancing act you have to do as an administrator. What are different types of faults that keep on happening all the time? Right. LG, LL, LLG, all L, LLL, that is 3 phase. You can design a system if you are bent upon which is fault proof. That means no fault takes place. Is it worth?
No.
It's not worth. There won't be any thrill in life if there is no fault. There is no need of any electrical engineer. And such a system will be very, very costly, very, very undesirable. It is like wearing a space suit in the winter so that you don't catch cold. No. Then you will be feeling there is a space on the earth, all moving in that. One who diffuses bomb, the bomb squad, they wear such dresses. Only they wear on earth, the space shuttle, when they go. So we take precautions. I am not saying that you don't take any precautions. All this earthing, grounding is what? It's a step in that direction, so that normally faults don't take place, and if at all they take place, you are safe. Nothing happens to the system. Why there is a fuse in houses? Why there is a fuse in any device? Because that's the weakest link. And if that is so cheap, a fuse wire is almost free of cost. So it is easy to replace. What happens in hostels? They put such a thick wire, pole fuse goes there, because nobody wants to go his room or his wing in winter when they use heaters, which is not allowed because that load is not provided for. But students use heaters. I am talking about old days when it used to be real winter. Now there is hardly any winter. So unbalanced fault analysis, neutral connection is very important. How neutral is connected? If it is a balanced, neutral current is not there. So all transformers or generators have neutral and it is properly grounded. And they considerably influence the fault currents and voltages. Whole thing is changed. Whole scenario is changed. Protective relaying and stability analysis are also influenced by neutral grounding. How do you ground a neutral is an art. Modern high voltage systems, system neutral is solidly or effectively grounded. What do you mean by solid grounded or effectively grounded? It is directly grounded. Something like direct online starting. There is no starter. Any motor less than 5 horsepower, you don't need any starter. Why do you need starter? The starting current is 5 times the full load current. I starting is equal to 5 times full load current. But that 5 times full load current is not large enough if the capacity of the motor is less. So we can tolerate that much amount of current. But if it is 100 horsepower, 25 horsepower, we start slowly and through starter. It can be star delta starter, it can be auto transformer, it can be anything. Similarly, here when we talk about solidly grounded or effectively grounded, what I mean? I mean it is grounded directly to the ground. There is nothing in between. There is no resistance, there is no reactance, there is no capacitance. It is just a big thick wire. There are specialized books written on grounding. You can see them. I have given their references. Generators are grounded through resistance to limit the fault, stator fault. Fault currents, static fault currents are there. It's also static fault currents or dynamic fault currents, which is not varying. From also for stability considerations, it is always better to ground through a resistance. What are the advantages of neutral grounding? Why should we do that? Because any grounding needs money, extra circuit. Voltages to ground are limited to the phase voltages. High voltages due to arcing faults or transient line to ground faults are eliminated. Over voltages, you are solving the problem of over voltages. Sensitive relays against LG faults can be used, line to ground. Now relays are numerical relays or computer relays. Gone are the days of electromechanical relays, static relays, solid state relays. Now we have electronic relays, computer relays or numerical relays. That is using software. If the value of the inductive reactance is such that the fault current IC balances the charging current, then the grounding is known as resonant grounding. So, if somebody asks you what is resonant grounding, when the value of inductive reactance XL is such that the fault current IC balances the charging current. And the grounding inductor, such an inductor which you have put in between neutral and ground, is given a special name in the literature, which is called Peterson coil. It's a very important term and is normally asked in interviews. What is Peterson coil? You should not look this way and that way. I don't know, sir. I read it sometime. Ungrounded neutral systems lead to, suppose you leave neutrals ungrounded. What happens? You want to save money for Peterson coil.
Phase voltages are converted to line voltages.
Okay. This is the arcing fault voltages. That is more important. So, this will lead to serious arcing fault voltages. Serious arcing fault voltages will be there if you don't ground the neutral. Peterson coil should be used for such systems operating with isolated neutral. What are the 5 different methods for neutral grounding? There are 5 methods. Anyone? Solid or effective grounded, from where we started this story. This is okay or it is effective if x1 by x0 is less than 3. What is X1? Positive sequence reactance. What is X0? Zero sequence reactance. Normally, zero sequence reactance is very high. It is 2.5 times the positive or negative sequence reactance. This you must have learnt in your fault chapters. And if you want to use resistance, then the condition is X0 upon X1 should be more than 3. For small I charging, low voltage, short line, SL is short line, LV is low voltage. Short line means no T network, no pi network, no capacitance, less than 100 kilometers, 80 miles. Reactance you use also for grounding. We use voltage transformer for grounding. We use zigzag transformer for grounding. What is zigzag transformer? Wherever there is a delta connection, there is no neutral available as such. So, there you have to use the zigzag transformer whenever there is a delta connection. And delta connection is a practical connection. It is not a theoretical idea or a fiction. Another important topic, corona. You must have heard of corona. As the AC voltage on a line conductor increases beyond a certain limit, a point is reached when a pale violet glow appears on the conductor's surface. What sort of glow? Pale violet glow, with accompanied by hissing noise. And story doesn't end there. There is ozone also coming along with it. So, it is a 3-pronged attack on a conductor. There is a glow, there is a noise, and there is a gas formation, which is ozone, O3. High voltage will always have an electric field. This electric field, what does it do? It ionizes air near the phase conductor. Minimum potential difference required between conductors to start ionization is called disruptive critical voltage. That is a minimum potential difference required to start this process, is called VD. And when that potential difference is available, we say corona is formed. And if you want to see that corona, then it will still go higher, and that is called visual corona. And the line voltage must exceed this VD, and that line voltage is called VV, visual corona. The potential gradient G0 at which a dielectric disrupts fully, that is, dielectric strength of the material is spoiled. That is called dielectric strength of the material, that gradient. What is that dielectric strength of material? The potential gradient Z0 is called dielectric strength of material at which point? At which a dielectric disrupts fully. What is the value? For air, such a value is 30 kV maximum peak per centimeter at NTP, normal temperature and pressure. The pressure is 76 centimeter of mercury at 25 degrees centigrade. So, dielectric strength is proportional to air density. Air density is defined as 3.92 B upon 273 plus T, that is absolute temperature, capital T. B is a pressure. Right? Potential gradient Z is V upon R ln D by R. So, Vd, the disruptive voltage, is 30 by root 2. Why root 2? To bring it RMS. It was maximum value. M0 R ln D by R kV RMS line to neutral. This M0 is called irregularity factor or surface or stranding factor. Three names are there. Irregularity factor is a noun and adjectives are irregularity, surface, stranding. All three mean the same thing. Shape of the cross section of the wire and on state of the surface. For smooth polished wires, M0 is 1. Chances of corona is minimum if it is smooth.
Higher voltage is required.
Yes, higher voltage. That is why chances are low. But if it is rough, then M0 varies between 0.92 to 0.98. If it is stranded, then 0.8 to M0, 0.88. Stranded means like this. It's not smooth. So, VB is 21.1. What is 21.1? 30 by root 2. Root 2 is 1.41. Root 3 is 1.772.
1.73 to 05088.
Huh? 1.73 is enough. Don't go beyond. M0 delta R 1 plus 0.3 upon under root delta R. Right? ln D by R kV RMS line to neutral. Again for MV, 0.72 local corona, if it is 0.82 general corona. Why do we use bundle conductors? If you recall, one of the answers which we gave for using bundle conductors is to reduce the chance of corona, because the E goes down and therefore radius goes up.
Electric strength decreases.
Yes.
That's it.
And corona is proportional to electrical state of the atmosphere, number of ions, size and charge per ion, air density, physical conditions, construction of line. These are all the factors you have to mention the moment the question is list the factors on which corona formation depends. Now, corona is not something which you will welcome.
Corona loss is there.
You see?
For high voltages, it is useful.
Well, I am coming to that. Normally, the undesirable features of corona, there is always plus and minus, whatever happens. There is a power loss, there is a harmonic currents, which is not proportional to voltage, is not psi, which is non-sinusoidal. Harmonic currents is non-sinusoidal voltage, and radio interference. So, while designing line, you must consider corona. How do you get the power loss due to corona?
Peaks formula.
Peaks formula. Let us come to Peaks formula. Power loss under fair weather conditions is given by PC. PC is power loss due to corona. 240 by, this is an empirical formula, there is no derivation, given by a gentleman called Peak, P-E-E-K. F is a Hertz, 25 R by D, V minus Vd whole square, 10 to minus 5 kilowatt per phase per kilometer. This is kV to neutral RMS. Luckily, the power loss is very small, hardly 1 to 2 kilowatt per kilometer for 500 kV. This is a bundle conductor. It increases rapidly with bad weather. Weather is bad, the corona loss increases. You can no longer ignore it. If it is a frost, it's the worst condition that can happen for conductors, which normally comes in US and any cold countries. What is RI? Not regress imprisonment. It is radio interference. Aviation, marine signals, broadcasting, all gets affected because of corona. As this young lady was talking about good points about corona, there is something good out of any evil also. You must have read, you must have written essays on the benefits of war. What does war do? It improves new technologies, it brings in. But for Second World War, there have been no atom bomb. There was no need. So, practical importance is corona reduces magnitude of high voltage steep fronted waves due to lightning or switching by partially dissipating them as corona loss. Thus, it acts as a safety valve, and you may ignore, you may not have any safety device like lightning arrestor. LA is not Los Angeles, but lightning arrestor is avoided because of corona. So, it acts as a safety. So, there is a, people ask you what is the practical importance of corona.
So it's also used in insulation testing.
Right.
It's specially used for insulation
Yes.
testing.
So, with this, we finish today's lecture. Any points you want to have, anything you want to raise, any queries, any suggestions? Yeah.
So what is the difference between ground point and the neutral point?
Ground?
Basic difference.
Yes, that question you should not have asked. I will
Ground
take
is
it.
always a geo
Getting
potential
confused,
and
sir.
neutral
Sometimes ground neutral.
It can be same, and if you have a resistance in between, it is not same.
Then it is not.
ground is always at
So
zero
why,
potential, but neutral is not.
Need not be. I will not say neutral is not. It need not be.
But
So
ground is always at 0.
Yes.
Earth is always at 0.
Yeah, that's it. It is because it is a reference point, like a slack bus. So it is a reference point.
So why not practically a two-wire line is only used, where neutral is grounded. Finally.
Yeah.
No, in three-phase system you can't use two-wire line. Two-wire line you can use only DC system. This question used to be asked in earlier times. Compare the copper required for 2-wire, 3-wire, 4-wire, etc., etc. Used to be a very regular question in universities.
कौन सा book है मोटा?
Sir, what is the local corona and general corona?
That you read.
Sorry.
Yes, we have only touched the topics so that you don't forget them. They are very important topics.
Okay.
Don't just get lost into bigger topics like load flows, economic operation, stability. They are more practical. They are very much a practical engineer have to know these things because they take all the time.
So, but why it can't be used like in a AC single phase system? Why only two-wire line can't be used where neutral is grounded?
This we'll talk after the class.